Hello, medical students. In this video, we will continue our MCAT physics preparation by resuming our discussion of motion along a straight line, linear motion that is. And then we will expand things a little to talk about motion in two-dimensional space in the context of projectile motion. And then we'll discuss center of mass, which is a concept that allows you to simplify certain mechanical problems. Now, resuming with linear motion, we're talking about graphs describing linear motion. And of course, the interpretation of graphs is something that's very important, not just in the context of motion problems. For instance, if you had somebody on an IV and you were giving them medicine through the IV, then you could draw a graph that would tell you how fast they were getting the medication and how that was changing over time. And that would be essentially the same type of graph as one of these motion-related graphs, but it would be interpreted in an entirely different way. So being comfortable with interpreting graphs is something that is going to go far beyond just this specific motion-related context. So I've drawn a motion graph here. Now this is motion along a straight line, and it's drawn in the plane. And the reason why we have two dimensions, the plane here, two dimensions instead of just one dimension, is because one of the dimensions is being used to represent time. And later when we talk about this graph machine idea, I will go back to this topic. But what the idea is that the vertical direction here measures your position, and the horizontal direction measures when you are at that particular position. So I've drawn a particular graph here, and the problem is to describe the motion which is encoded in this graph. So what we could do is we could say, okay, well, so this is the time in seconds. So at 0 seconds, you start out at a position of 0 meters. So this would be, if you're moving back and forth along a line, you would choose a particular point which you say is your 0 point, and that would be where you would start. Now, between 0 and 2 seconds, see, between 0 and 2 seconds, I have this straight line segment here. So this is 0 to 2 seconds. What's happening there? Well, you move, your vertical distance here is telling you how far you've moved and in what direction. And you've moved out to 2 meters. So you've moved, and I have the positive direction here oriented up. So I'm going to say moved up 2 meters. And you can tell more details. The fact that the line here is straight instead of being curved like this or curved like this, the fact that the line is straight is telling you that you're moving at a constant velocity. So in particular, if you're moving at a constant velocity and you're moving 2 meters, then that would mean that after over 2 seconds, that would mean after 1 second you move 1 meter, as you see here. And then in the next second, you move another meter, exactly. So you moved up 2 meters at a constant velocity, and I'm not going to write the rest of those words. Now between 2 and 3 seconds, and I'm not going to keep writing seconds, 2 to 3 seconds, you're stationary. See, you don't move at all, you stay at 2. So you're stationary. And then what happens between 3 and 4 seconds? So 3 to 4. Well, the line is straight, so you're moving at a constant velocity, and you're going in 1 second, you're going from a position of 2 to a position of, I can write 4 in here. So you moved up 2 meters. Now notice here you moved faster because you're going from 3 to 4 seconds. That's just 1 second. Whereas here you went in 2 seconds, you went up 2 meters. So that's why the slope of the line is steeper there. And then 4 to 5 seconds, you see here you're stationary. So 4 to 5 here, you're stationary. Again, draw a line here. Now between 5 and 6, what's happening? 5 to 6. Well, you started out at 5, you were a distance of 4 meters up, and you moved back down to 0. This would be 0. Put my 0 here. So you moved down. Now notice now you're moving down. I left out the word moved. So here you moved down. How many meters? 4 meters. Now notice how steep this line is compared to that one and that one. You're moving much faster here because over 1 second you're moving a total of 4 meters. And then 6 to 7, well, you move up 1 meter. Now here's where it gets interesting. What happens between this point here and this point here? Notice on the vertical direction here, you're not moving side to side at all. So this, now remember, this is measuring time. So here this says it's 7 seconds, so you're going along this way in terms of time. It's 7 seconds, you have this point here which is at 1 meter, and then you have this point up here which is at 3 meters. And it still says 7 seconds. This here is impossible. This is not possible because you would be in 2 places at the same time, or else you would be moving infinitely fast to get from this point to this point. So you could say that this violates Einstein's theory of relativity because you move faster than light. Which is, just kind of a silly, it's sort of a tongue-in-cheek thing. I just wanted to give you an example. You can't draw any old curve or graph on here and have it make sense. I mean, for instance, you can't go like that. It wouldn't, here, once again, here you'd be in 3 places at the same time. And that's just a matter of what the variables in the graph mean. The fact the horizontal variable means time, it means that, certainly there can only be one vertical value for each one of those horizontal values. Otherwise, it wouldn't make any sense. So, so this is happening at 7, and this is not allowed. So, practically speaking, you're not going to see graphs that have something like that in it, but it's useful for teaching purposes to show you, what that would mean if you did have that. So then in between 7 and 8, then you would be stationary. All right. So we've analyzed this graph here in pretty close detail. Now the next thing I want to do is make a remark on something that's said in the book, and this is one of those points where the book says something that's not quite accurate, and so I need to point that out to you. What the book says is that it says that if you draw a curve that represents displacement, and so I'll just draw a So this is, I don't know if you want to call it a typo or problem or issue or whatever, but this is worth pointing out. So if I have a graph like this, and this is going to be displacement again, going this way, and you could have it be in meters again, and this could be time again, and this could be in seconds, if you like. Well, what the book says is that the area under the displacement curve, so this is the area under the curve. And by under the curve, it means between the curve and the axis here. Over here, of course, that area is actually below the axis, so it's above the curve. But the area under the curve, so what the book says here is that the book says that this is meaningless. And that's not true. It's not meaningless. So what does the area under the curve mean? Or more generally, the area between the curve and the axis. So if I take, so I could take this area here. So this is this whole area from this point up to this point here. So I'll call that A1. And I'll call this area here A2. And then I'll call the whole length of this interval here, from that point to that point, I'll call this L. Well, what's actually the case is that the area A1 minus A2, so this is A1 minus A2 divided by L is your average displacement. That's what it means. Notice over here I'm going to talk about area versus signed area. So this word sign means a positive sign or a negative sign. And so here the A1 has a positive sign associated with it, the A2 has a negative sign associated with it, which is why there's a plus sign here and a minus sign here. And that's because this area is above the axis and this area is below the axis. So this quantity here, the area divided by the length of that interval here, it is important because it's telling you your average displacement. Now, the average value of something is an important quantity. For instance, take something like blood pressure. You know, if you can drive up your systolic blood pressure by exercising, for instance. So if you exercise, you know, say your resting blood pressure is 120/70, you know, say you're healthy or whatever, and say that you exercise, you raise your heart rate and you get your systolic blood pressure up to 165, you know, for instance. Well, that's not bad. I mean, it's good for you to exercise. If your average systolic blood pressure was 165, that would be too high. So you care about the average. You know, it's like you go to the doctor and you're nervous because you are afraid what he's going to tell you is something, and he takes your blood pressure and it's high, and you say, well, it was only high because I was nervous. And then he says, okay, well, go to Walgreens and get a blood pressure cuff and test it at home and bring back and show me what it is on average, and then I'll believe you if it really is low. And so you bring back this readout of the blood pressures, and they're all high. And he says, well, what's going on here? And you say, well, on that one, I was nervous because I was preparing for a test. And on this one, my girlfriend was giving me a hard time. And on this one, I ate a bunch of salt, and on, you know, and so on. Well, he's going to say, we're going to have to put you on blood pressure medication because your arteries don't care why your blood pressure is high. They just care if your blood pressure is high on average over a period of time. But in any case, it would be unfortunate if you thought that the area under the displacement curve doesn't have a meaning, because it has an important meaning. And that is that area, provided that you have the proper signs divided by the length of the curve, is the average value of the displacement. And the same would be true if this graph was measuring something else, like blood pressure or like, you know, any number of things. So I needed to clarify that little point. Okay, so let's move on and talk about this graph machine. And so the book has this useful little idea. So this is in the book. And this is this thing it calls a graph machine. And it's in there around page 11 or page 12 or something. And so what the idea is, and I'm not going to try to represent this really, but you have sort of, have you ever seen one of those machines that laminates? Like, for instance, if you make a card, like your insurance sends you a card and it's one of those cheap paper cards in the mail and you want to laminate it, and so you put it through this lamination machine. And so it's this little thing where you run a piece of paper through it. And so you run a paper, you know, through the machine. And so the paper is pulling through this way, and this thing is the machine, it goes through this way. Well, the idea of the graph machine is an imaginary machine. I mean, seismographs, actually, for earthquakes, they work in a similar way. You may have seen this thing where there's this roll of paper that's rolling through, and then the little pen on the seismograph goes back and forth, and it makes this sort of jagged line. But here what you imagine is that there's just this kind of a slider, and there's this point on the slider, and the point can move up and down on here as the paper is pulled through. Now, so as the paper is pulled through, well, that position of that point on there will trace out a line. I guess I drew this the wrong way because this is the part of the paper that's already been pulled through. So what this would tell you, so you're pulling the paper through this way, and this will tell you, well, the point started out here, and as I dragged the paper through, it moved up here, and it made this little mark on here. So the whole point of that exercise is just to give you an idea how this one-dimensional motion up and down, like what we were talking about in that last graph, can be converted to a picture that has a two-dimensional aspect where the horizontal direction is measuring time. That's what the point of this graph machine idea is. Okay, so that's worth looking at just to understand conceptually what's going on. So let's move on to talk about velocity versus time graphs. And so this is a different kind of graph, and you have to be careful because it matters what the axes of the graph are representing. So now instead of displacement, this is going to measure velocity. And I can say this is going to be in meters per second. And then this way is going to measure time. So this is time, and this can be in seconds. And now I'm going to draw, and I can put details on it like I did on the last one if I want to. This looks a little inaccurate. Draw these little tick marks on here. Okay, so I can say, now here I'm not going to start out at 0. I'm going to start out at 2. This is 1, 2. And I'm going to continue this way, so it's going to be flat here. And then I'm going to go this way. I'm going to actually have this go down as well, like I did last time. On the previous displacement graph, I never had the curve go below the axis, but it could. Well, on the previous one, it was that curved one that went below like that, because I was talking about this area under the displacement. The one I did, the detailed one that I started out with, it didn't go beneath the axis, and it could. It certainly could. So let's have that happen over here. Let's have this go, say, like that. And so so this is a velocity versus time graph. And once again, the task is to describe the motion. Now let me ask you this. Where this is flat here, does that mean that the particle or the object or whatever the thing is measuring, does that mean that it's stationary? No. Because this is saying the velocity is constant. But that doesn't mean the displacement is constant. See, you have a constant non-zero velocity. The velocity is 2. So that means the displacement is increasing. So if I doctor this a little bit, it's funny, I drew that, now I'm erasing it. So here, so I'll put in my, I guess I'll put my numbers here so I can fit them. 1, 2, 3, 4, this would be 5 and 6. So between 0, so at 0 seconds, this starts out at, so this is moving up, at 2 meters per second. Now, we don't know where it starts. This velocity graph can't tell you that. It just tells you velocity. It doesn't tell you position. So we don't know where it starts. We don't know the position, or displacement rather. It means the same thing. But we don't know the displacement. We just know how the displacement is changing. That's all we know about this. Okay, that's at 0 seconds. So 0 to 2 seconds. What's it continues what it's doing here. You know, it starts out here. I guess I could have just said 0 to 2. So that's abbreviated. Let's say 0 to 2 here. That means a 2, not a minus. So this is between 0 and 2. I will just write the word 2, I guess, so as not to confuse you. So 0 to 2 seconds is moving up at 2 meters per second. Now, from 2 to 3, notice that the velocity is changing. So now velocity changing, that means acceleration. So this velocity changes from 2 meters per second to 3 meters per second. And I can add the detail that the velocity is changing constantly. But I'll just say that. It's a straight line here, so the straight line means that the acceleration is constant. And really, we're limiting ourselves to constant acceleration setting throughout all this. And then from 3 to 5, this is supposed to be a straight line. It doesn't quite look straight. But so 3 to 5, the velocity changes. So it changes from 3 meters per second to 0 meters per second. So it slows down at a constant rate. It slows down and it stops. See, remember on the last graph when it was stopped, that meant the displacement graph, that was where it was showing a horizontal value. Here it stopped, at least for an instant, when it hits the axis here, because that's when the velocity is 0. So that means a different thing. And then 5 to 6. 5 to 6. Here, the velocity changes to minus 1 meters per second. Now, what does the minus 1 mean here? It means it's moving down. So it's from here to here, it's accelerating downwards. So that's what the negative value velocity here represents. Now, we can also talk about the area under the curve, or more generally, the area between the curve and the time axis here. So I'm going to scribble over what I had here. But that's this area here and this area here. Now, so what this area, and I could once again call this A1. I'm going to call this here A2. So this is area. Now, A1 minus A2 means one thing, and A1 plus A2 means another thing. So what A1 minus A2 means is, well, I shouldn't say means, I should say is. So A1 minus A2 is the change in displacement. And this is from the time starting out at 0 to the time going to 6 seconds. And then A1 plus A2 is total distance traveled over that time. over that same time, 0 to 6 seconds. See, these two things are different, and this one's bigger because it's a plus there instead of a minus. Because what happens is this whole time the curve is up above the axis, the velocity's in the positive direction, which we've agreed is going to be the vertical direction here. And so that means it's moving up. This whole time it's moving up. Well, in this little part here, it's moving down. So what happens, if you watch what the particle does, it's going to move up for a while, it's going to move up for a while, and then it's going to slow down to a stop here. And then it's going to move down a little bit. So the total displacement's not going to be quite as far because it moves back down a little bit to where it started. Whereas the total distance, if you were thinking about like a little beetle going along and walking that path, the total distance it travels is a little bit further because it travels part of that distance twice. It goes all the way up and then it comes part of the way back. And so when you add those two distances together, you get something that's a little bit bigger. So so this is this idea of area versus signed area. So area, if you just add all the areas between the curve and the axis for this velocity versus time graph, if you're just adding up all these areas, in this case there's just two, this one and this one, then you'll get the total distance traveled. If you add up the areas with signs, where the positive sign happens if the area is above the axis and the negative sign if it's below the axis, then you will get the change in displacement in that time interval. So that's what's different. Now the book doesn't really talk much about acceleration versus time graphs, and I don't think I'm going to either, simply because I don't see how that's really likely to show up in problems. I'll just make a brief remark. Of course, if you've taken calculus, so this is just a remark. And we're not having a calculus perspective here, but velocity is the derivative. You may not, if you haven't had calculus, you may not even know what that word means. So this is the derivative of displacement. And so what the derivative really means in this context is just the slope of that displacement curve. You know, if I have this displacement curve like I do this one before, at any particular point, you know, say here I have what the slope is, you know, so the slope of that, how steep it is. Here, so if this is displacement, well then here the displacement is decreasing quickly, and so that means that you have a velocity that's a large value in the negative direction. And then it will turn out that acceleration is the derivative of velocity. So these are related in that way. And then you could also talk about, so this is differential calculus. You could also talk about integral calculus in this context if you wanted to. And in that case, what you would do is you would say, well, velocity is the integral of acceleration. And in this case, integral, once again, if you haven't had calculus, you might not know what that means, but this means area in this setting. And then displacement is the integral of velocity. So all these little remarks they're making in the book about the slope of the curve or the area under the curve, they're really talking about calculus. And this area would really be a sine area in this context. But that's all I'll say about that part.